on there. It's just swappage. Okay, so the key step then is just acetyl-CoA is inert. We're going to have to add it, that methyl in, right? The CH3. I mean, what is acetyl-CoA? Anybody? You got the S-CoA, and then you got what? You got a carbonyl, right? And then you got what? The methyl, right? 2 carbons. Carbonyl, where all the magic happens normally, right? Whenever we do anything with acetyl-CoA, it's usually at that carbonyl, and we're kicking out the S-CoA, right? The S-CoA wants to leave. It's a leaving group that wants to go away, and we're bringing something in there. Well, this time, we got to work at the other carbon, and it's a methyl, and methyl's just, inert as dirt, right? So we got to do something. So we do something fancy with CO2, activate it with biotin, put the CO2 on there, so now we got something on that end that wants to go away. Right? Just like the S-CoA wants to go away, now we got the CO2. It's ready to go away and just resonate its little heart out. Right? That's why it drives the reaction, because it's going to resonate and be lower energy. So we have that there, and we're primed for that carbon-carbon bond then between the CO2 and what it's now methylene to add. Okay? So you just do that step over and over again where you make this funny creature, malonyl-CoA, and then it becomes malonyl-ACP. So you do that again and again, you just add it to your growing chain. Right? And then we reverse, and then, y'all should have this down by now. Like, what cofactor do we use? What reduced cofactor do we use when we're biosynthesizing? NADPH. So we're going to use that as opposed to what? And an FADH2, right? So that's the difference. So we're going to do that, and then we're just going to go through. Okay, so what are we now? We're oxidized, right? So our very first step when we condense, the very first step we're going to do is bring in that hydride ion from NADPH. Now we got a hydroxyl. Okay, so I was talking to Kwame about this on Friday, that once electrons are on oxygen, be it whatever, a hydroxyl, a carbonyl, whatever, those electrons are on oxygen because you can't take those electrons and pass them to oxygen, right? That's the whole point of generating energy, right? We're going to pass them down here to molecular oxygen. So when we're going through the TCA cycle or whatever, whenever we have an oxygen on carbon, those electrons are spoken for. Okay? They belong to that oxygen. So as we're going through and we're making fat, we're just going to take those away. And in their place, we're going to bring in more, what?
Bird.
Say it. Wow. Yeah, hydride ion. We're bringing in more electrons, right? So we're starting with something. That's all we're doing. We're just taking this carbon skeleton and we're adding in electrons that we can harvest when we need them. Right? What?
We just haven't studied yet.
Okay, but that's when you look at these pathways, just look at it and go, okay, there's no electrons to be had there, right? And so when we're making fat, we're going to do that first reduction. The carbonyl goes to a hydroxyl. We're going to take that hydroxyl away. It becomes what? Water, right? As soon as you put a hydroxyl ion in water, it becomes water, right? Unless you're pH 14 or something, but it just becomes water. So you just take that away, it's water, and then you've got that carbon there waiting to bring in 2 more electrons. And then you're done, okay? So you're just loading with electrons, removing the water.
Hey, I'm a little confused. You were saying that once electrons are on oxygen, they're on oxygen for good?
Yeah.
But then during this process, we are taking them off?
No, so we're taking, so it depends which way we're going. I mean, those electrons are going with the oxygen. So when you see a COH, right, that carbon-oxygen bond, those electrons are going to go away with the oxygen, is what I'm saying.
So they move with it.
They move with it, because oxygen, I mean, I want to say because of the electronegativity, but compared to carbon, hydrogen, they're shared, right? Those electrons in a carbon-oxygen bond, they're all on the oxygen, and oxygen's going to be happy. That's why you do have some small amounts of OH in water, right? Because it's happy to do that. Okay? So that's why when you go through the TCA cycle, you're just systematically dismantling carbohydrate, right? So you have carbons with OH and carbons with a CH, right? And with a CC, right? And so that kind of brings up pentose phosphate pathway. What step? So remember, we kind of broke down pentose phosphate in terms of not it's a pathway, but we had, okay, what's the first part?
Glucosinate.
And I mean, what happened there?
NADPH.
We made NADPH, but how do you describe that process?
Decarboxylation. Decarboxylation. Oxidation.
I thought you said, John House, you said like animalism or something like that. No, what, okay, what was that overall?
Oxidation reaction. Redox.
Help me out.
You said redox.
The first step of pentose phosphate pathway, what type of?
You have oxidative and you have non-oxidative.
Yeah, but okay, so we're in oxidative then. So what's the first thing that happens?
If we generate NADPH, it's oxidation.
Barry, come on.
Oxidative decarboxylation.
Yes.
You said that?
Okay. Yes. Oxidative decarboxylation. Okay. So that carboxyl group went away, right? Because all of the electrons there were on oxygen. We couldn't do anything with them. They went away, and we grabbed, what did we grab along in the process? Hydride. We grabbed the hydride ion, and it went to NADPH, NADP plus, right? Which is the, okay, but what does NADP plus do? Okay.
It regulates the process.
Thank you. It's the key regulator, right? It's how much of that is available. In steady state, I think it was 70 to 1 reduced to oxidize. But as that ratio shifts where you get more than 1, then that's going to activate. That's the sole means of activation is just the availability of the substrate. Okay? All right? So, okay, so back to this breakdown. Then we have the oxidative decarboxylation that we went from a 6 then to a 5, right? I mean, that's why it's decarboxylation. We went from a 6 to a 5 because we've seen this oxidative decarboxylation where the carbon, like one of these carbons now, is bonded to oxygen so many ways that it's no good to us anymore. So it just goes away, right? And then we grab the hydride ion. So what was the other example we had of something like that? An oxidative decarboxylation. Pyruvate. Yeah, so the pyruvate dehydrogenase, right? And then we saw that again, the same chemistry, same type of chemical situation later in the TCA cycle. I think it was alpha ketoglutarate, am I right? But we saw that again, okay? So back to pentose phosphate. See, are we just going through pathways, or are we going through concepts and processes and similarities, and you see? So the oxidative decarboxylation, we went from 6 to our 5. We're going to use our 5 a lot of the time to do what? You're a cancer cell, you need lots of nucleotides to make DNA, right? So we're going to use that 5 to make the nucleotide biosynthesis. And then we got the NADPH for primarily fatty acid biosynthesis. Okay, so then we're there, and then the next set of enzymes that are unique to pentose phosphate pathway do what? Yeah, so rearrangements, but just simple isomerizations, right? So there are, that isomerization from what, because we come out with ribulose or something, right? And we want to make ribose too. So we do that. So then we got those two forms. Then we get into using which two enzymes for all the other rearrangements.
Trans keto.
And those are unique. We've not seen anything like them anywhere else because, Ryan? Oh, you got your mouth full, so you can skate. Okay. Come on, anybody. What? Well, the names are the opposite, but no, I've heard it.
Carbon splitting. They move the carbons. Break them.
2 words.
Sounds like.
But breaking, right? It's like, you've probably never even seen, maybe you've been to a museum, seen Tinker Toys. They were a big part of old folks' upbringing, right? Do you even have Tinker Toys? No. Now you do this in 3D graphics or something, I don't know. But Tinker Toys, right? You just break them apart and move them around. But that was all highly unusual because we don't see it. We see these decarboxylations, or we see activation of CO2 to add it back on, but otherwise, breaking carbon-carbon bonds is not something we do. So transalylase, transketolase, those are very remarkable reactions catalyzed by those two enzymes, and they're absolutely required so we can swap around 5, 7, right? What was it? 3, 5, 7? Isn't it 3, 5, 7 to get what? What numbers? 3 and 6, right? And then the 3 and 6 we can do stuff with. We can go into energy, or we can go into gluconeogenesis, or right? Okay, so I think that's covered. What else? Yeah, so I mean, clearly you can see this oxidation and reduction stuff. Get a handle on it. If it doesn't, if it's just not readily apparent to you, I think that's.
Dr. Druck,
Yeah.
I mean, one thing about not memorizing is it's very difficult to discuss some of those topics without having the correct nomenclature and names. Is there any way you can go through and maybe look at a couple of processes and pick out key intermediates that you just say, you need to know how to talk about this key intermediate, you need to know how to talk about this key intermediate?
Yeah, well, but I mean, we already have in that I don't know, we pretty thoroughly went through pentose phosphate pathway in my view, and we never really said much more than what was happening. Right?
So is the size, correct? Like, is knowing the size of carbon molecule, is that, I mean, for that one it seems okay, because you know you're going through the carbon molecule.
No, I really don't think, except for knowing what these key regulatory enzymes are. Like some of the board questions, I think there was one that